Next chapter, Approximation of Area. Now, areas of regular plane figures are calculated using definite formulae. There are, however, no formulas for calculating the areas of irregular plane figures. We can only estimate the area, which means the value obtained is not an accurate one. It could be an underestimation or an overestimation. In this chapter, we shall look at the area under curves. When a graph is plotted, it assumes an irregular shape and the area to be calculated must be defined. For instance, consider an equation y is equal to x squared minus 3x plus 5. If we were to plot this curve, it will start from infinity and end in infinity. And this is because there are as many values of y as there are values of x. And unless we are given the range of values of x, x has values from negative infinity to positive infinity. So to be able to plot this graph, we need a range. For example, we plot the values of x from negative 2 to positive 4. We say the range is negative 2 less or equal to x less or equal to 4. Now we can form a table of values for x and calculate the corresponding values of y. From here, we plot the graph. But to find the area, again it must be described. For instance, we'd say the area bounded by the curve, the x-axis, the line x is equal to negative 1 and the line x is equal to positive 3. This is the region whose area we want to find. First method, the trapezium rule. The trapezium rule is used to estimate the areas of irregular shapes and particularly the area under curves. Consider a graph of this nature. Suppose you wanted to calculate the shaded area under the curve. The two vertical sides AC and BD are parallel to each other and are perpendicular to the x-axis. If we can estimate the curved side AB to be a straight line, we would roughly have a trapezium. We can calculate the area from the formula a half A plus B times height, so we shall have a half into AC plus BD times CD. This area is an estimation because in reality, the side AB is not a straight line. If we were to have a straight line, it would be this. This time, the area will be an overestimate because it includes the unshaded part between the straight line and the curve. To reduce the error margin and get the curve to be as close as possible to a straight line, we divide the figure into smaller trapezia. Consider this speed time graph. Suppose we want to find the distance covered after 30 seconds. We need to calculate the area under the curve up to time 30 seconds. In other words, it's the area bound by the curve, the y-axis, the x-axis, and the line x is equal to 30. If we assume the entire region to be one trapezium and that the curved path is a straight line, then the error will be quite enormous. To minimize that, we divide it into smaller trapezia, say like 6 of them. We then calculate the area of each one of them and then find the total. By reducing the size of the trapezia, the curved part is almost a straight line, not perfect though, and so the area is still an estimate. Area of the first trapezia, A1, will be given by a half A plus B times height, that is a half times 5 plus 18 times 5. That gives us 57.5. A2, a half into 18 plus 26 times 5 gives us 110. Third area, a half into 26 plus 32 times 5 gives us 145. A4, a half into 32 plus 36 times 5 gives us 170. Area 5, a half times 36 plus 38 times 5 gives us 185. Area 5, a half times 38 plus 40 times 5 gives us 190. Total area will be equal to 57.5 plus 110 plus 145 plus 170 plus 185 plus 190, giving us 862.5 square units. And so the distance covered is 862.5 meters. Notice that we divided the area into 6 trapezia. If we had divided it into 12 units, the area will be a more accurate estimate. The more the number of trapezia, the more accurate the estimate. With that, we can now derive the formula for the trapezium rule. Now, consider this velocity time graph we had previously. We said we can assume side AB is a straight line, but then the error will be enormous. So we divide it into several portions. Suppose we divide this area into 5 equal parts. The vertical lines are called ordinates. We have ordinates y1, y2, all the way to y6. The width of each small portion is h units. If we assume the units to be small trapezia, we can find the area of each one of them and then add them up to get the total area of the shaded part. Area 1, a half into y1 plus y2, the ordinates, times h. Area 2, a half into y2 plus y3 times h. Area 3, a half times y3 plus y4 times h. Area 4, a half into y4 plus y5 times h. And area 5, a half into y5 plus y6 times h. Total area is the sum of all of them, a1 plus a2 plus a3 plus a4 plus a5. We can factorize a half h. So we shall have a half h into y1 plus y2 plus y2 plus y3 plus y3 plus y4 plus y4 plus y5 plus y5 plus y6. That will give us a half h into y1 plus 2y2 plus 2y3 plus 2y4 plus 2y5 plus y6. Looking at the terms in the brackets, only y1 and y6 occur once, so we can isolate them. We have y1 plus y6 in one bracket, plus we factorize the rest. 2 into y2 plus y3 plus y4 plus y5, everything times a half h. Then we factorize h, so we have a half into y1 plus y6 in one bracket, plus y2 plus y3 plus y4 plus y5 in another bracket, everything times h. This is the general formula for finding the area of the curve. Notice that the region is divided into 5 trapezia by 6 ordinates, that is y1 to y6. In general, if a region is divided into n trapezia, each of with h units, the number of ordinates is n plus 1, and the estimated area using the trapezium rule is given by area is equal to a half into y1 plus yn plus 1 in one bracket plus y2 plus y3 plus y4 all the way to yn in another bracket, everything times h. This is the trapezium rule. Going back to our graph, we can calculate the area, this time using the trapezium rule. We have 6 trapezia, and so we shall have 7 ordinates, y1 to y7. Using the trapezium rule, the width is 5, that is h is equal to 5. So we shall have 5 into a half times 5 plus 40 plus 18 plus 26 plus 32 plus 36 plus 38. That gives us 5 plus 40 is 45 times a half is 22.5. So we shall have 5 into 22.5 plus 18 plus 26 plus 32 plus 36 plus 38. That gives us 862.5 square units, which is equal to 862.5 meters. The same answer we got. We can use the trapezium rule to estimate the area under any curve. For example, plot the graph of y is equal to x squared minus 2x plus 6 for the range of x from minus 2 to positive 4, and use the trapezium rule to find the area bound by the curve, the x-axis, the line x is equal to negative 1 and x is equal to positive 4. To plot the graph, we need a table of values. The range of x is minus 2 to positive 4. From the equation y is equal to x squared minus 2x plus 6, we can calculate the corresponding values of y from the values of x that we have been given. If we do that, we get 14, 9, 6, 5, 6, 9, 14. If we draw the curve, this is it. The area is from this line, x is equal to minus 1, and this one, x is equal to 4. We can have 5 trapezia, and so we shall have 6 ordinates. The ordinates are basically the y values in the table we have here. The width h is 1. So using the trapezium rule, area is equal to 9 plus 14, that is y1 plus y6, plus 6 plus 5 plus 6 plus 9. That gives us 11.5 plus 6 plus 5 plus 6 plus 9, giving us 37.5 square units. Now, since the ordinates are the y-coordinates, using the trapezium rule doesn't require the graph to be drawn to find the area. For example, using 5 trapezia, estimate the area under the curve y is equal to minus x squared plus 6x plus 2. The x-axis, the line x is equal to 1 and the line x is equal to 6. We form a table of values. The values of x, 1 to 6. They are the only ones we need. If we calculate the corresponding values of y, we shall have 7, 10, 11, 10, 7, 2. The width is 1 unit, that is h is equal to 1. So area will be equal to a half into 7 plus 2 plus 10 plus 11 plus 10 plus 7, everything times 1. We have 4.5 plus 10 plus 11 plus 10 plus 7, giving us 32.5 square units. The next method for estimating the area of irregular shapes is the mid-ordinate rule. Now, consider this curve. The curve has been divided by the grid into 6 trapezia of width h units. We called the vertical length ordinates. Suppose we draw new ordinates through the midpoint of each trapezia to meet with the curve. Since these new ordinates pass through the midpoint, they are called mid-ordinates. We can calculate the area of each portion by assuming it to be a rectangle of width h and height equal to the length of the mid-ordinate. The total area under the curve is then the sum of them all. So area is equal to first portion h times y1 plus second portion h times y2 plus h times y3 all the way to h plus y6. Factorizing h, we shall have h into y1 plus y2 plus y3 plus y4 plus y5 plus y6. This is the mid-ordinate rule. Because the height of the strip is assumed to be that of the mid-ordinate and therefore a rectangle, there is a part that will be inside the rectangle and another part outside it. And so there is an overestimate and an underestimate occurring simultaneously, and they are assumed to compensate each other. For example, calculate the distance traveled between 0 and 30 seconds using the mid-ordinate rule. So we find the area bound by the curve, the x-axis, the y-axis, and the line x is equal to 30. So the mid-ordinates are 6, 9, 13, 18, 25, and 34. You can read that from the graph where the mid-ordinate meets the graph. So area is equal to, the width is 5. So we have 5 into 6 plus 9 plus 13 plus 18 plus 25 plus 34, giving us 525 square units. And so the distance is equal to 525 meters. Final example. Plot the graph of y is equal to x squared minus 2x plus 6 for the range of x from minus 1 to 4, and use the mid-ordinate rule to estimate the area under the curve, the x-axis, the line x is equal to -1 and x is equal to 4. First things first, to plot the graph we need a table of values. We have the values of x and we substitute them in the equation to get the corresponding values of y. We shall have 9, 6, 5, 6, 9, and 14. We plot the graph. Now we don't need these coordinates anymore. We want the mid-ordinates. You can read them off the graph or you can calculate them directly from the equation of the curve. We know the first mid-ordinate will be at x is equal to -0.5, the second one x is equal to 0.5, 1.5, 2.5, and 3.5. If you substitute in the equation of the curve, you will get 7.25, 5.25, 5.25, 7.25, and 11.25. And so you see, if the question does not require you to draw the curve, you need not to draw it. You can calculate the mid-ordinates directly from the equation of the curve. The width h is 1 unit, so area is equal to 1 into 7.25 plus 5.25 plus 5.25 plus 7.25 plus 11.25. That gives us 36.25 square units, and that is the area under the curve.
I think one of the problems with math is if you aren't strong in it, you end up with weak spots in the foundation. And so if you want to build on that, if you want to go in and major in it or to do honors in it, you really do need a solid foundation. And so if you don't have it, if you've had a bad experience with math, you tend to sort of slough it off, and that's a serious mistake, I think. I believe with the right resources and help, most people can learn most of the math that they need to learn. But in almost any class that you go into, you need to make sure that you're at the starting point, People come in with different backgrounds, different preparations, and so you're not all on the first day at exactly the same place.